Now we are going to see the topic servo motors. The motors that are used in automatic control systems are called servo motors. When the objective of the system is to control the position of an object, then the system is called servo mechanism. So what is servo mechanism? If there is a system and if the objective of that system is to control the position of some object, then the system is called servo mechanism. The servo motors are used to convert electrical signal, that is control voltage, applied to them into an angular displacement of the shaft. Okay, so this servo motor will convert the electrical signal into some angular displacement. Types of servo motors. Now, the servo motors are classified into three types: AC servo motor, DC servo motor and special servo motors. So this DC servo motors is divided or classified into two, that is, one is armature control motor, another one is field control DC servo motor. Now DC servo motors. So first in DC servo motors, first we are going to see the transfer function of armature controlled DC servo motor. So the speed of a DC motor is directly proportional to the armature voltage and inversely proportional to the flux in field winding. Okay, so the speed is directly proportional to armature voltage and inversely proportional to flux in field winding in a DC motor. In armature controlled DC motor, the desired speed is obtained by varying the armature voltage. So we are going to find the transfer function of armature controlled DC motor. So in armature controlled DC motor, the speed is obtained by varying the armature voltage. So this motor is an electromechanical control system. The motor is having electrical part and mechanical part. So we are saying it as electromechanical. The electrical system consists of armature and field circuit. So this is a electrical part, or this is a field part, and this is a armature part. This is a shaft. Okay, this is angular displacement. J is moment of inertia. Okay. So the mechanical system consists of the rotating part of the motor and the load connected to the shaft of the motor. So since this is a armature controlled DC motor, for analysis we are taking only the armature circuit and the field circuit is neglected in armature controlled DC motor. So the armature controlled DC motor speed control system is shown in the figure. This IA is nothing but armature current, this VA is nothing but armature voltage, and RA is armature resistance, and LA is armature inductance. IA is armature current, VA is armature voltage, EB is a back EMF, KT is a torque constant, T is a torque developed by motor which is given in Newton meter, theta is angular displacement of the shaft, J is a moment of inertia of the motor and load, and V is a frictional coefficient of the motor and load, and KB is a back EMF constant. Now the equivalent circuit of armature is shown in this figure. So the equivalent circuit consists of the armature resistance RA, the armature inductance LA, and the back EMF EB. This is a armature voltage VA. Now we are going to apply Kirchhoff voltage law to this loop. So here positive to negative is taken as positive and negative to positive is taken as negative. So it will, when applying KVL, you will be getting IARA plus LA into DIA by dt plus EB is equal to VA, or in other words we can say plus IA into RA plus LA into DIA by dt plus EB minus VA is equal to 0. Now, torque of the DC motor is proportional to the product of flux and armature current. Since flux is constant in this system, why? Because this is armature controlled DC motor, so flux is constant. So the torque is directly proportional to the armature current IA. So T is proportional to IA. So T is equal to KT into IA. So this KT is nothing but a constant. The mechanical model of mechanical system of the motor is shown in this diagram. Now we are going to write the differential equation of this system, mechanical system. So J into d square theta by dt square plus B into d theta by dt is equal to the applied torque T. Okay. Now the back EMF is proportional to the angular velocity of the shaft. So EB is proportional to d theta by dt. So back EMF EB is equal to KB into d theta by dt. The differential equations governing the armature controlled DC motor speed control system are the first one. This equation we got by applying KVL to the armature circuit, that is IARA plus LA into DIA by dt plus EB is equal to VA. T, next one, the torque T is equal to KT into IA, and next one J into d square theta by dt square plus B into d theta by dt is equal to T. Next, the back EMF EB is equal to KB into d theta by dt. Now we are going to apply the Laplace transform to the differential equations with the initial conditions. So we are going to apply the Laplace transform to the first equation. So it is nothing but IA of S into RA plus LA into S into IA of S plus EB of S is equal to VA of S. Now we are going to apply Laplace transform to the second equation, that is T is equal to KT into IA. T of S is equal to KT into IA of S. We are taking this as equation number 6. Then we are applying Laplace transform to the differential equation d square theta by dt square plus B into d theta by dt is equal to T. So we will be getting J into S square into theta of S plus B into S into theta of S is equal to T of S. We are taking it as equation 7. So back EMF EB is equal to KB into d theta by dt. So EB of S is equal to KB into S into theta of S. On equating equation 6 and 7, so we will be getting, because in equation 6 and 7, the one side you are having T of S, so we can equate the other two sides. So we will be getting KT into IA of S is equal to JS square plus BS into theta of S. From this we are calculating I of S. Okay, we are taking it as equation 9. Now equation 5, we are substituting in this is equation 5. In this equation 5 you are taking IA common, so we will be getting RA plus S into LA into IA of S plus EB of S is equal to V of S. Now we are going to substitute the value of IA of S and EB of S in this equation 10. So while substituting we will be getting like this. So here the transfer function, what is transfer function? Transfer function is nothing but Laplace transform of output by input. In this motor, the output is nothing but the angular displacement theta of S. The input is nothing but the input armature voltage VA. So we have to find theta of S divided by VA of S. So we have calculated theta of S divided by VA of S. Now we have expanded we have multiplied this J square by Vs with this Ra plus S into La, we will be getting like this. Okay. After that, from this we are taking S common. Then we are bringing it to in this form, and the transfer function of armature controlled DC motor can be expressed in another standard form. So it can be expressed in another standard form. The standard form is nothing but, this is the standard form. So Kt by Ra into P divided by S into 1 plus Sta into 1 plus Stm plus Kb Kt by Ra into M. Here La by Ra is nothing but electrical time constant and J by B is nothing but mechanical time constant. This is nothing but the transfer function of armature controlled DC motor.